So I hope that you can see the slide. And today we are going to have the practical total nitrogen in soil and plant samples. So here soil, you understand what is soil, and in plant we will estimate total nitrogen. So let us see how we can do it and what are the objective of this practical to determine total nitrogen in plant and soil samples, and the role of nitrogen in plant growth, and relationship between total gel-dal nitrogen and crude protein content in different plant tissues and certain numericals. So overall, just now we discussed what is total nitrogen. So you can see total nitrogen is organic nitrogen plus inorganic nitrogen. Inorganic nitrogen, that is mineral nitrogen. So maybe in ammonical form, nitrate form, nitrite form, or some other inorganic forms. But you know, ammonical nitrogen and nitrate nitrogen, these are the predominating or dominating kind of inorganic nitrogen. But you can also have NO2, means nitrite nitrogen, which is quite insignificant, which is quite in insignificant quantities. Means it is by nature has made it very temporary kind of ion in the soil, because it becomes toxic to the plant. Little higher concentration of NO2 or nitrite is toxic to the plant. So therefore nature has made it very ephemeral, very temporary, and it is immediately converted to nitrate. So these are the three forms which are mineral or inorganic nitrogen. At any given time, 95 to 99% of nitrogen in soil is in organic form. You can see predominantly it is organic form of nitrogen in the soil. And in a relatively stable soil organic matter, that is humus, which on an average contains 5% nitrogen. This humus contains about 5% nitrogen. Living organism also contain, and mostly microbe. So these are different organic forms like your plant and animal residues, some partially decomposed matter, and relatively stable matter, that is humus, and of course living soil organism are also there. And mineral nitrogen in soil accounts for approximately 2% of total nitrogen in soil, and even maybe less than that. So mineral nitrogen means you can see ammonical nitrogen, nitrate nitrogen, and nitrite nitrogen. They account for about 2% or less than 2% of the total nitrogen in soil. So this 2% is exact figure, but it may vary. It is not that exactly every soil will have 2% as inorganic nitrogen or mineral nitrogen. It may range. Range may be 1 to 3% or something like that. So 2% is just very average or typical value of inorganic nitrogen in soil. Now, what are the organic forms? We know that organic nitrogen is 95 to 99% sometimes of the total nitrogen in soil. So in which form does it exist? So organic soil nitrogen occurs as proteins, amino acids, amino sugars, and other complex nitrogen compounds. So these are the forms of organic nitrogen in soil: proteins, amino acids, amino sugars, and other complex nitrogenous compounds. The proportion of soil organic nitrogen in these various fraction is, so they are not same. The level of nitrogen in these compounds may be different. So the proportion of, the proportion of soil organic nitrogen in these various fraction is amino acid 30 to 45%, bound ammonical nitrogen 20 to 35%, and acid insoluble is 20 to 35%, amino sugars 5 to 10%, unidentified 10 to 20%. So you can see relative proportion of different compounds, organic compounds which have nitrogen. Means whatever total nitrogen or total organic nitrogen is there, in that amino acid contribute 30 to 45%, and bound ammonical nitrogen is 20 to 35% of total organic nitrogen. Acid insoluble 20 to 35%, and amino sugars 5 to 10%, and unidentified is 10 to 20%. So these are the major forms of organic nitrogen. Now, most forms of organic nitrogen cannot be taken up by plants. So they cannot be directly taken up by plants. As you know, mineral theory of nutrition, which suggests that nitrogen or any other nutrient is removed in ionic forms. So in mineral form or ionic form, nutrients are taken up by plants, but a little part of nitrogen is also consumed or taken up by plant in the form of organic molecules. That is DON and SON. DON is dissolved organic nitrogen. SON is soluble organic nitrogen. So I will take a 20-minute extra, some other class on SON and DON, where I will teach you this. Organic nitrogen, you know, it is converted to inorganic nitrogen by mineralization. By mineralization with the help of microbes. These microbes attack the organic matter, which contains nitrogen, and it is mineralization which results in inorganic nitrogen. And it can happen other way around also. This inorganic nitrogen can also be converted into organic nitrogen through the process of immobilization. It depends upon the CN ratio of the organic material. So this also we will discuss in some other lecture on organic matter. Now overall you see it is mineralization which is converting the organic nitrogen into inorganic nitrogen. First step is aminization, then ammonification, and then nitrification. So through these three steps, you get inorganic nitrogen or mineral nitrogen. And let us see what are these steps. So nitrogen mineralization is through two processes. One is aminization and other is ammonification. So see aminization, what is happening? The organic nitrogen in proteins is getting converted into amino acids, amines, and urea. So these proteins are attacked by bacteria or fungi. These are heterotrophic bacteria or heterotrophic fungi. Can I ask you what is heterotrophic organism? Heterotrophic organism. What do you mean by this? Heterotrophic bacteria or fungi.
It depends on other for their food. Don't make their food by own.
Exactly, correct. So they are actually doing the job to get the food because they cannot synthesize food at their own. They want to eat the food directly. So these are heterotrophic bacteria or fungi which attack the proteins, and then it is converted into three forms: amino acids, amines, and urea. And plus CO2 is also released, you know, in decomposition. This is also kind of decomposition of organic matter where CO2 and energy is released. Particularly, this is shown under aerobic conditions. So heterotrophic bacteria dominate the breakdown of proteins in neutral and alkaline environments, while heterotrophic fungi predominate in acid soils. So hope you understand this aminization. These three compounds are formed: amino acids, amines, and urea. And then ammonification of these amino compounds containing amino group NH2. I think you know this is RNH2 represent amino group plus water hydrolysis, and there may be some organism here, and then it is converted to ammonia. So this ammonia can be lost. It can be lost from the soil, or if there is sufficient moisture in the soil, then it will get the water, and this addition of water to ammonia is hydrolysis. This is known as hydrolysis, and then ammonium is formed. So it will be, at least for the time being, it will remain stable because it is in ammonical form. The pH and water content of the soil will decide the fate of ammonia, what is going to happen to it. So we continue with the aminization and ammonification. The ammonium produced by ammonification is subject to several fates. Several fate means it can go into different pathways. One is that it can be converted to nitrite and nitrate by the process of nitrification. You know what happens in nitrification? Nitrosomonas convert this ammonical form to nitrite form, and then nitrobacter converts nitrite to nitrate form. And actually, they do not directly involve. These bacteria, Nitrosomonas and Nitrobacter, they release some enzymes, and that those enzymes catalyze, or those enzymes are necessary for conversion of ammonical form to nitrate form. Some of the ammonium can be absorbed by higher plants, particularly under aquatic conditions. Plants can absorb ammonical form and utilized by heterotrophic bacteria to decompose residue. So some bacteria can also consume this ammonical form available in the soil, and it is immobilization, means ammonia is just released through the process of mineralization, but it can be further consumed back by heterotrophic bacteria, and which is your immobilization. Immobilization can also happen. And some may be fixed as biologically unavailable nitrogen in the lattice of certain clay minerals, which is known as ammonium fixation. Ammonium fixation can happen, and then other route is that it can be converted to ammonia and released back to the atmosphere by the process of volatilization. So this ammonical form is not a stable form. It can go into different routes, and it can go to different routes simultaneously also. So means it is liable to be lost very quickly by different, except immobilization. Other routes you can see it will be, or ammonium fixation, it will remain in soil. Now, immediately after ammonification, conversion of organic nitrogen to ammonia, hydrolysis conversion in water of ammonia to ammonium is followed. So you can see this form, this ammonia is produced. This ammonia can escape the environment, but if moisture is there, water is there, the hydrolysis converts it to ammonical form. Ammonium and ammonia means, you know, your ammonia is formed. So whether it will stay as ammonia or it will be converted to ammonium. So ammonium and ammonia, nitrogen are closely related. They are very closely related. Ammonia is a gas, and at high pH levels, it favors this form, ammonia. If your pH is high, ammonia volatilization is high. So it favors this form. High pH favors ammonia form, and it can quickly escape from soil into the air. Ammonical form is a soluble ion and favored by low to moderate pH. If your pH is low to medium, or you can say neutral, then this ammonia volatilization will be less and nitrogen will be in ammonical form. So ammonical form is soluble ion and favored by low to moderate pH. At this pH or acidic conditions, the volatilization will decrease. Ammonical form is attracted to negatively charged soil particles held as an exchangeable cations in soil. So this ammonia can be absorbed by the colloids, whether it is organic colloid or clay colloid, but it can become part of cation exchange capacity. Thus, ammonium is a common soil nitrogen form and ammonia is not, because ammonia cannot stay in soil. If it is formed, it will immediately escape the soil. So ammonia is never a form of soil nitrogen, but ammonium is a form of soil nitrogen. Ammonium can also be trapped between the layers of clay minerals, which is known as ammonium fixation. This ammonium fixation I will deal if time permit and we do it, we'll see. Now, as you know, available nitrogen is mineral nitrogen, thus it is revision, mineral nitrogen, ammonical plus nitrate nitrogen mostly. And then available nitrogen also include potentially mineralizable nitrogen, which is from organic matter. Means what proportion of organic matter nitrogen or organic nitrogen can be immediately made available to the plants. Therefore, it becomes available nitrogen. In other words, it is also called as readily oxidizable nitrogen, or you can call it potentially mineralizable nitrogen, which is part of available nitrogen. So now you see some data about nitrogen. In general, 2% of organic nitrogen in soil is converted to mineral forms in a year. In 1 year, 2% of the organic nitrogen can be converted into inorganic form, range being 1.5 to 3.5%. Most nitrogen release from organic matter occurs during growing season, providing a continuous supply. Because in growing season, you have crop in the soil, demand is also there, demand for nitrogen is also there. So nitrogen which was there in the soil solution, or nitrogen which was part of cation exchange capacity or was exchangeable nitrogen, that will be taken up by the crop, and it will encourage further decomposition of organic matter, because these kind of forms, inorganic forms, organic forms, are in equilibrium in the soil. So if uptake is there, then the conversion of organic nitrogen to inorganic will be faster. So most nitrogen release from organic matter occurs during growing season, providing a continuous supply. And also during growing season, you will have sufficient moisture also in the soil that will improve the biological activity in the soil. So you will get more release compared to fallow soils. This is because the microorganism responsible for releasing nitrogen from organic matter require some soil moisture. So therefore, you can remember that conversion of organic nitrogen to inorganic nitrogen is faster under cropping condition than fallow conditions. So you can see little more background of organic and inorganic nitrogen, how these two pools are contributing towards mineral nitrogen or available nitrogen. See this central point. This is mineral nitrogen, nitrate and ammonium, 2% nitrogen in soil. So there are 2%. 2% nitrogen in soil means mineral nitrogen is approximately 2% of the total nitrogen in soil. This is one. And number two is that annually 2% of the organic nitrogen is converted into inorganic nitrogen. So these are 2% are two different values, and they have two different meanings. 2% means your out of total nitrogen available in soil, total nitrogen, 2% is inorganic nitrogen. And in 1 year, 2% of the organic nitrogen is broken, is decomposed into inorganic or mineral nitrogen. So mineral nitrogen is here, and this mineral nitrogen can come from fertilizer. It can also come from organic nitrogen breakdown. It can mineralize. So mineralization by microbes can result in inorganic nitrogen. And this inorganic nitrogen can be taken up by plants. And then plants can leave certain organic matter in the soil in the form of roots or leaf fall, litter fall, and then that can become part of organic nitrogen. So this was the little background of soil nitrogen. And now we will go to the this method after one more slide. So healthy plant foliage generally contains 2 to 4% nitrogen. Now we see the nitrogen percent in plants, because method is same. Method for estimation of total nitrogen in soil and total nitrogen in plant material is same. So healthy plant foliage generally contains 2 to 4% nitrogen on an average, depending on plant species and age of the leaves. So what happens? Plant species means leguminous plants will have more nitrogen in their biomass than the cereal plants or other plants. And normally younger plants, younger age, they have more nitrogen percentage than the old plant. So nitrogen is an integral component of many essential plant compounds. In plants also, it is made up of amino acids. the building blocks of all proteins, including the enzymes, nucleic acids, chlorophyll, RNA, DNA, all these organic materials contain nitrogen. A good supply of nitrogen stimulates root growth and development as well as the uptake of other nutrients. So today we will learn how to estimate the nitrogen, total nitrogen in plant as well as in soil. So up to now, do you have any query, any question, anything, any point you want to discuss? Is everything clear to you?
Yes, sir. Clear, sir.
Yes, sir.
Good. So now we know the method is Geldahl method. Geldahl method, K-J-E-L-D-A-H-L. This Geldahl method has three different steps. First is digestion, means you need to remove the carbon, hydrogen, nitrogen by wet digestion. This is known as wet, W-E-T, wet digestion. You need to remove carbon, hydrogen, oxygen so that nitrogen comes in the mineral form. And once it has come in the mineral form, that is ammonical form, then it can be distilled. Then it can be distilled by process distillation. So then distillation will come. And once the ammonia is distilled or nitrogen is distilled, then it can be titration. So there are three different steps in estimation of total nitrogen by Geldahl method: digestion, distillation, and titration. So in digestion, how it is done? Organic nitrogen in sample, that is mostly protein, is converted to ammonical nitrogen by digestion with concentrated sulfuric acid. So sulfuric acid will digest or it will oxidize. It will oxidize carbon or it will decompose the carbon or organic nitrogen containing potassium sulfate or sodium sulfate that promote this conversion. So potassium sulfate or sodium sulfate will act as a catalyst. It will speed up the process. Then after this nitrogen has come in ammonical form, then we will do distillation. So ammonical nitrogen is determined from the amount of ammonia liberated by distillation of the digest. Digest is your material in the Geldahl flask where you have used sulfuric acid and this digestion accelerator. Then now you use alkali, that is sodium hydroxide, for distillation. And in the beginning, you see this distilled ammonia is collected in boric acid and mixed indicator. Boric acid and mixed indicator, this has pink color, pink or red color of the mixed indicator. And that color, when ammonia is absorbed in the boric acid mixed indicator solution, its color changes to bluish green after entry of ammonia into the boric acid. And then you are going for the titration. So ammonia absorbed in boric acid containing mixed indicator is determined with a standard acid. Any standard can be used as a titrant, like sulfuric acid. Normally we use sulfuric acid, but other acids can also be used. Now this bluish green color will again come back to the pink red color on titration when you add acid into it or when you add titrant into the boric acid solution. So boric acid mixed indicator with ammonia changes back to the pink or red color at the end point of the titration. So these are three important principles of determination of total nitrogen in soil or in plant. Or you can see more here. More here, these three different steps are very clearly shown. Unfortunately, you are not doing it, but it would have been very good experience for you to enter the lab and do it by yourself. So really you are missing it. Anyway, so in this case, you can take certain quantity of soil and put in the Geldahl flask. This is a Geldahl flask It was made by Geldal, and the neck is long, so that when it is bumping, the liquid or materials will not come out. When you boil it, if neck is short, then the materials can come out when you put acid and boil it on the heater. So this is your Geldal flask. You put soil sample into it, and then you put acid, a certain quantity of sulfuric acid, and then you add potassium sulfate or sodium sulfate, that is digestion accelerator. And then first of all, you can keep it for some time. Keep it for some times, let the thing settle and sulfuric acid react. And then you can heat it up, and then after 30 minutes approximately, or say 40 minutes, it will be digested. When you get very clean or clear liquid in this, when there are no suspended particles, then you can ensure that your digestion is complete. Sometimes incomplete digestion is also there. Students don't see it seriously, but it should be very clean and clear. So this is called as your digest, and it contains your ammonical form of nitrogen. Nitrogen in ammonical form. And then you go for distillation. So this is the distillation flask. In this distillation flask, or you can directly take this same Geldal flask here. Same Geldal flask you can take here, and then put 40% NaOH. Just NaOH solution is required. And this complete set is your distillation assembly. The complete set is distillation assembly. So when you put this digest here on the burner, and you put some sodium hydroxide into it, and immediately plug it, and then the reaction will be happening, and ammonia will be liberated. Here, up to here, it will be NH3. Then it will move from here to here. Here you will get condensation, some cooling system, and then it will become converted to ammonium hydroxide. And this ammonium hydroxide will fall here. It will fall here, and it will be collected in the boric acid. So initially, the color of the boric acid mixed indicator was pink or red. And when ammonia starts entering into it, the color changes to bluish green. And then you will go for titration. You will remove this conical flask from here. It is bluish green in color. And then you will have a burette, and then you will do titration. When you titration with the help of sulfuric acid, and then the color of the boric acid mixed indicator will convert back to pink or red, pinkish red. So that will be your end point. So this is how we do this estimation by Geldal method. Do you have any question at this point of time? Geldal method, digestion, distillation, titration, very simple procedure. Now see the reagents. So reagents are catalyst, mixture, or digestion accelerator. So catalyst, mixture, or digestion accelerator, it can be made by 10 gram anhydrous sodium sulfate. So one can take sodium sulfate and 1 gram pure dry copper sulfate pentahydrate per sample. So this much quantity per sample will be used. So one can make a bulk, make it in bulk, and then for every sample you can use this much of 10:1 ratio, 10 gram of anhydrous sodium sulfate and 1 gram of copper sulfate. Then mixed indicator, how to prepare the mixed indicator? So it is prepared by having 0.1 gram bromocresol green plus 0.07 gram methyl red indicator in 100 ml of 95% ethyl alcohol, ethanol. So this is how one can prepare the mixed indicator. Then boric acid solution. It is 4%, then 40 gram boric acid per liter of distilled water. You can mix, and then 5 ml of mixed indicator solution added to each liter of boric acid solution. So this is how boric acid solution can be prepared. Sodium hydroxide for distillation, 40% sodium hydroxide solution using nitrogen-free sodium hydroxide flakes. Flakes are like this, like your finger. It is not in powder form, it is in the form of flakes. It should be allowed to stand for 24 to 48 hours. So students should handle this solution very, very carefully. You can injure your skin or your body parts if it spills and it comes to your clothes or any body part. So very, very dangerous chemical. And it is when you prepare it, you cannot use fresh solution. You need to wait for 24 to 48 hours to get it cooled down. So cooling takes long time, and you can use it after 24 to 48 hours only. And there may be certain precipitates like sodium carbonate and other impurities that can be removed later. Concentrated sulfuric acid of specific gravity 1.84 required. Salicylic acid and sodium thiosulfate, they are also required, but they are required only for soil. When you are doing total nitrogen analysis in soil, then you need to have salicylic acid and sodium thiosulfate. These two chemicals are required to reduce the nitrate. If you want to estimate ammonical nitrogen, nitrate nitrogen, organic nitrogen, all forms of nitrogen, including nitrate nitrogen, then you need to have these two chemicals, salicylic acid and sodium thiosulfate. If you don't want to include nitrate, you don't need to have it, these two chemicals. Similarly, in plant analysis, total analysis of nitrogen in plant, you do not require these two chemicals, salicylic acid and sodium thiosulfate. So next slide, we can end it here and we will join on next link.